going to introduce our second speaker. So our second speaker is Dr. Michele Folchi from IIT Italy from Dynamic Leg System Lab. And he's going to be talking about locomotion strategies for legged robots. Go ahead, Michele.
Hi, thank you for inviting me to this workshop. Do you hear me properly?
Yes, that's perfect.
Okay, yeah. I am Michele Folchi. I'm a researcher at the Istituto Italiano di Tecnologia, and today I will talk about locomotion strategies for quadruped robot or legged robot in a more broad sense. First, let me give you some motivation on why we would like to use legged robots. If we compare with the vehicles with wheels, we see that, for example, animals show an excellent versatility and mobility and superior locomotion performances. And in our vision, we would like to design robots to flank humans in dangerous environments and operations. So in legged robots, we think about several applications that range from disaster response, search and rescue, nuclear decommissioning, inspection, construction, where the robots can be used for collaborative tasks to handle payloads and move around the loads. And finally, we got interested into space application, and we see here we can play a role in terms of exploration and in the part of preparation of the infrastructures. So driven by this motivation in my lab, that is the Dynamic Leg System Lab, that is led from Claudio Semini, we got 13 years of experience in designing hydraulic quadruped robots and locomotion algorithms. Looking at the timeline, we see we designed our first prototype that is called IQ, that stands for hydraulic quadruped, back in 2010. Then we came out with a second version, improved one, which was able to self-right himself when it was falling. It's called IQ2 Max, a small version, IQ Mini. And then we designed also the hydraulic arm that we put on top of a quadruped platform, creating a center. Finally, the last born in 2019 is called IQ Real. IQ Real is the fruit of a joint collaboration, a joint effort in collaboration with a multinational company called Moog, that is a world leader in motion control solutions for aerospace. And IQ Real is completely power autonomous, Wi-Fi teleoperated, and completely untethered. And you can see from this video the superiority of hydraulic robots in heavy-duty application. And in this case, the plane was heavy, 3 tons, the weight of the plane. And here we have, I'm showing you some more highlights on IQ Real. That thanks to his improved and big range of motion is able to walk with the belly down, you see in the bottom left video, and address rough terrain, climbing upward, climbing up and down from stairs. So it's able also to deal with the human structure environments, which is a very important point for legged robots. But let me talk now about some challenges that you can face when you work with legged robots from the scientific point of view. First, these robots are heavily constrained. This means that they have friction constraints, unilaterality constraints. That means that the leg can only pull and not push, can only push and not pull on the ground. They have actuation limits and the kinematic limits. And all these constraints pose a severe limitation on the availability kernel. So we need to be able to carefully design our locomotion algorithm, taking this into account to avoid falling. The second point is the dynamics that is unstable. It's a floating-based robot, and we are able to control the center of mass only through the action of the contact forces. This means that you have an hybrid dynamic that is not differentiable across the contacts, and this creates problem whenever we are using it in an optimization problem. Another important point is that they have many degrees of freedom. We have up to 12 for a quadruped robot and about 50 for a humanoid. And this big number of degrees of freedom creates, if these models are used in optimization, results in a big size of the states and a big number of constraints, and therefore in a high computation time. So in my research, I found out that a model-based approach, rather than a machine learning approach, was achieving good performances in practice because the simplified representation of the robot was good enough to predict future behavior and also guarantees constraint satisfaction in the future. And here there is a sketch of our locomotion framework that we use for to traverse rough terrains. And we see on the left side, we have the input coming from a navigation algorithm or the user that is setting the desired velocity of the robot with a joystick. And then we have the planning block that generates the references of the center of mass and of the trunk orientation that are given to the whole body controller. Then the whole body controller takes care of the stability, of the locomotion stability, setting desired torque references for the low-level torque control. We close the loop on the state estimation, so we need also a state estimation algorithm that fuses odometry and proprioceptive sensor outputs, and in order to close the loop for the control. Due to the limitation of this in this talk, I will talk mainly about the planning block here and how do we design trajectory for the center of mass and the orientation of the trunk. So in our vision, as Frank properly said, we need to be able to handle disturbances, handle inaccuracies, model uncertainties in an effective way. And in our vision, we found out that a three-layer locomotion layer, according to the quality of the visual feedback, is a good compromise to achieve this target. At the bottom, we have a blind locomotion layer, which is based on heuristics that is always on. And according to the availability of the visual feedback, we can improve and generalize this control, this planner. So I show you that what we are able to do with this locomotion, heuristic locomotion planner. We are able to traverse a variety of terrain with the interfaces within them, addressing a certain degree of roughness. We have stones that can have the size of the kind of stones you can find in space exploration application. And we achieve this thanks to three main ingredients that are the haptic touchdown. That means that we stop the motion of the leg only whenever the contact is really achieved. So we have 4 sensors or torque sensor at the joint for which we are able to estimate the contact forces. We do one-step replanning to recover from errors, from pushes, from instability of the rocks, of the bricks, for example, here. And then we have a strategy that tries to align the trunk of the robot to an estimation of the terrain inclination. Okay, that was great, but we wanted to improve this heuristic strategy in order to be able to generalize to every kind of terrain and every kind of motion, because the heuristic works well in this kind of terrains, but doesn't work, for example, for jump or other kind of motions. In addition, the heuristics has no awareness of the future. It just look at the actual state of the robot, while to be able to be sure that we will fulfill the constraints in a prediction horizon, we need to consider future states evolution. For this reason, optimization-based numerical optimization is a good tool that to address this problem, because it takes into account a model to predict the future behavior of the robot, and is able to find the optimal motion that satisfies the constraints. However, we need, for example, a map of the terrain to estimate the normal at the contacts, the inclination of the terrain under the contacts. For this reason, optimization specifically for legged robot has some issues. We know that legged robots have many degrees of freedom, and this means that they have a high number of states and constraints that makes the computation time explode. On the other hand, we have unstable dynamics, so we need to be able to be reactive in time to avoid falling, and these are conflicting requirements. For this reason, people in the robotics community start to use lower dimensional models, and that are reduced models that capture only the predominant dynamics of the robot, mostly the central mass one, and they have limited number of states and are mostly linear or easy to be convexified. We see that the two most famous reduced models that are used in locomotion are the linear inverted pendulum, which is 2-dimensional, and the centroidal dynamics that is 6-dimensional. So we have a reduction of with respect to the 12 joints of a quadruped of more than half of the state variable. However, even if these simplified models speed up optimization, they lack of descriptiveness. In particular, because they have no knowledge of the joint-related coordinates, they cannot model that limits that are defined at the joint level, like, for example, the actuation of the torque limits or the kinematic limits. For this reason, we had the idea to translate the joint limits into limits to the motion of the central mass. We came out with the idea of the feasible regions. The feasible regions can be used for planning, and they are tools that are able to guarantee the feasibility of the trajectories, while still allowing the use of lower dimensional reduced models, lower dimensional models, thus retaining the fast computation time feature that they have. We start to illustrate the seminal work of Timothy Bretl on friction regions that first define the friction region as the set of the central mass location where the robot is able to counteract gravity, so be statically stable, and satisfy friction constraints. To compute this region, he used a point mass model that allowed, for example, to have non-coplanar fit. So it was suitable for rough terrains. However, if you look on the left, there are we see that the friction region coincides with the subpower polygon only when the fit are coplanar. While if we have non-coplanar or non-collinear fit, the stability region where these two constraints are satisfied can differ significantly from the support polygon. Moreover, we notice that also the actuation limits were playing a role in restricting the region. In particular, whenever you load the robot, for example, like here with an external load, the torque will increase and get closer to the actuation limits. And this will restrict the locus of position of the central mass that are feasible without hitting the actuation limits. Thanks to this idea, we improved the friction region, adding taking into consideration the actuation constraints. And we came out with the feasible region, which is a reduced version of the friction region, where also where if you plan your central mass trajectory, you are sure that the actuation limits will be satisfied. And this is a work made in collaboration with my student, Romeo Solino. But the main point was the actuation limits are defined at the joint level, and we had to define at the fit level because our point mass model had no knowledge of the joint variables. So we use to do that a mapping. We map these torque limits through the Jacobian of the foot into force polytopes. These four polytopes are the set of admissible contact forces for which the actuation limits are satisfied. And we see here in this simulation that these four polytopes are changing with the configuration of the joints because the Jacobian is depending on the joint configuration. And if you look at this simulation, we see that the friction region, the light gray one, is changing with the contact condition, but the feasible region, because of the Jacobian, is also changing with the robot configuration while moving. We thought that we would have problems into that because of computation time, but we found out that the feasible region was still suitable for online planning because we were able to compute it at a rate of 66 Hz. Of course, the friction region that only takes into account friction constraints was way faster. So we decided to use a feasible region for planning. We need to remark that feasible region is an intuitive way, but powerful to design feasible trajectories because it's a 2D region, and you're sure that if you plan the trajectory in this region, the joint constraints will be satisfied. However, in these first experiments, we didn't plan the whole trajectory with the region. We just take into account the target location of the center of mass. In this situation, we have, since we have a static crawl that swings one leg at a time and move the trunk whenever it's on 4 legs, the most critical situation is when the center of mass is only on 3 legs because the load is distributed only on 3 legs. Therefore, we plan the target of the center of mass not in the feasible region, but in a shrink version of the feasible region. Why? Because this way we are able to ensure some robustness and reduce unnecessary motions, like the backward motions. So we are able, thanks to the feasible region, to also set the degrees of robustness we want to have in our locomotion, according, for example, to the roughness of the terrain. If you want to be more cautious, have a more cautious locomotion, we can set a higher shrinkage factor. The feasible region could also be used for foothold planning. Let's say we have a candidate set of footholds, and we compute the feasible region for each one of them, and we can select the one that has the biggest inscribed area, for example. And we see here in the simulation both the planning of the central mass and of the foothold using the feasible region, and we see that whenever the terrain becomes critical, the robot might take smaller steps, like the right-hand side, right hind leg of this, the last step. And on the bottom right, we see an experimental validation with a robotic platform of the region. An important extension that we added recently was the fact to take into account external branches. So think about the robot is pulling a cart or is pulling a load, and we see that the feasible region is shifted forward. And this makes the planning of the robot to do such that the robot will lean forward naturally, as a force of a human will do whenever he's pulling a load. This opened up to a new field of locomotion, which is rope-aided locomotion. We got this idea for casualty, and I found out that actually rope is mandatory for addressing and climbing very steep terrains. Because if you look at the left-hand side, we have a terrain where the inclination is smaller than the friction coefficient. And we have an equilibrium of the contact forces with the gravity. But whenever the inclination of the terrain becomes bigger than the friction coefficient, then the contact forces are no longer able to compensate gravity because the cone boundaries go beyond the vertical. And the blue line, it's the force that is not compensated and that creates slippage. While if we use a rope, we're able to compensate the tangential component of gravity and have the contact force in the middle of the cones. And we also increasing robustness because we have more range of errors. This is a snapshot of a simulation where the robot is climbing down a slope of 45 degrees. And this is a simulation where we further make it difficult, like having to reduce the height to enter in a tunnel that represent a cluttered environment, typical inspection template. The same idea can be used for space application. Think about the exploration of a crater. We can set up an anchor at the edge of the crater, and through a rope, the robot has a hoist on board, and it will rappel down, taking steps according to the online computed feasible region. And we'll be able, ideally, to address very high inclinations. Think about a dual robot system where we have a rover and that deploys the quadruped platform, and the anchor could be set up directly on the rover itself. And with a torque-controlled brushless motor, we can control the torque on the hoist, and so we can release the rope in a way that is in accordance to compensate just the gravity. Till now, we didn't discuss about the last point was missing, that are the kinematic limits. If you think about these kind of complex terrains, they might require changes in the orientation and in the height that can make the joints reach their limits. For this reason, we came out with a similar idea, that is the reachable region. Unfortunately, I cannot give you the details on the computation of this, but they are in the papers, they will be in a paper that is on preparation. And this reachable region is the set of kinematically feasible center of mass location, for which the robot is not hitting any of the limits. And I would like to show you how is changing the reachable region with the height and with the orientation. And we see here that the reachable region, differently from the feasible region, can be a non-convex region. We see that whenever the red ball, that is a projection of the center of mass, hit the boundary of the region, it means that one of the joints hit the limits, the kinematic limits. To summarize, we briefly presented the friction region, incorporated the actuation limit, and created the feasible region, and adding the external branch computation and intersecting with the reachable region, we can define the extended feasible region, that is a comprehensive region that takes into account friction, actuation, and kinematic constraints. And using this region, we were optimizing orientation. In this way, we are without this orientation optimization using the feasible region, it would not be possible to cross this kind of very complex terrain without hitting the limits, or in terms of actuation or kinematic limits. I am at the end of the presentation. Thank you very much for your attention, and I'm glad to reply to your questions.
All right, thank you very much, Michele, for the great talk. Again, just a quick comment to the folks participating in this workshop. Feel free to use the chat window to ask questions during the talk, and then we'll get to those at the end of each talk. So I have one question for you, Michele, and I might have missed this one, but have you guys looked into the interaction of this robot with what we call flowable ground, or like, for example, granular media?
We did some experiments with the, actually there is a talk in ICRA of another work we did on a foam. So walking on a foam on a compliant terrain.
Okay.
But we still didn't do any work on granular media actually. I think they are very difficult to model first, and certainly is an open problem to deal with this kind of terrain. We were able to walk on rocks that are rolling away, so they're not fixed, they're not consolidated terrains, and this thanks to the replanning feature of our algorithm that helps to enables the robot to recover from the tracking errors that are, for example, introduced by the fact that one rock the robot put the foot on is rolling away, so it's creating pitching error, for example, or rolling error.
I see. Perfect. All right, thank you very much. So I guess since we don't have any other questions, I'm gonna go ahead and thank you, Michaela, once more, and
You're welcome.
then thank you very much. And so now I'm going to introduce our next speaker,